Hi everyone, I'm glad to be here with you today at Percona Live. I'm going to talk about security and traceability on distributed database systems today with you. We're going to talk about uh, PostgreSQL mainly, but it also applies to other DBMS. And we will talk about proxies and how uh, all components are bring together. I'm Julien Riou. I will be your speaker today. I'm a DBA since 2012, working on the database team as a technical leader at OVHcloud since 2015. And you can see uh, all the talks, all my previous talks on my personal websites and a way to contact me if you need to ask me questions on the link uh, below. I work at OVHcloud, which is a major cloud provider in Europe. We are based in France, and we have multiple services. We sell bare metal servers for high performance computing. We also provide cloud computing services and a lot of other services. And the main thing they share, the common thing they share is they all rely on internal databases to provide a way to control the service. So if uh, any database goes down, the main thing the main impact of the service is we can't control them anymore. So it's very important for us to keep databases up all the time. So high availability is very important for us. Internal databases are about 60 clusters, um, mainly PostgreSQL and MySQL. We are an open source databases um, shop. We have around 3,000 applications talking to the databases. And the particularity we have is our main users are our own developers. So we can talk with our developers and move forward together to bring the better service for our customer. And it's uh, spawned on around 500 databases, more or less, worldwide. So there is not only one single data center, we have data centers around the world. We have a strong requirement for security. So every time we build a service, we keep in mind that we have security to comply, and that allows us to have PCI DSS compliancy on some services that to store and manage credit card informations. And there's also Secnum Cloud, which is a French compliancy, which is more or less as we require more or less security requirement as PCI DSS and more. So security is a key point for us. On this talk, we'll see some context, what we manage, and we how our components are bring together. We'll talk about the security problems and traceability problems we have faced, and what kind of PostgreSQL solutions we can implement, and we see those limitations, and the we'll see some generic solutions we can apply on any databases. And we'll sum this up together in a conclusion. So the context. Um, High availability is very important for us to have the less impact negative impact on the service, on the way we manage the service. So we have found a solution to have the maximum availability on our database systems, which is composed of a virtual IP managed by KeepAliveD. This virtual IP can be moved on one box to another and it can be moved around. We have load balancing in place. So the client traffic goes to the virtual IPs and go to the load balancing. And the load balancer is responsible to forward traffic on the node, which can be a primary or a replica at any point of time. So load balancing can move traffic on the good role on the good node at any time. And we have automatic failovers managed by Patroni, which is a famous uh, high availability solution for PostgreSQL. And this infrastructure allows us to have a failure on a node at any time and to forward the traffic in very few seconds to another node and still have the service available. And as you can see on the schema, it's distributed on multiple nodes. And the main problem we have is the usage of proxies. It fits on between the client and the server, and we use Proxy, which is a very good software, um, but it's not transparent. That means the client IP address will be altered by the proxy. The databases, we will see the proxy and not the client directly. So without proxy, it goes like this. All the clients talk directly to the primary here, for example, and the primary will see the IP address of the client 1, for example, and client 2 and 3 directly. So there is no problem. And when there is a proxy, the clients talk to the load balancer, and the load balancer talk to the node, any node. So, and the load balancer are uh, placed on uh, every node. So the first node will see either itself or the neighbor. So IP address are loose in the process. And we have a particularity at OVHcloud. We manage a lot of legacy systems that are in place since um, 20 years now, more or less. Um, we have multiple applications that share the same database user to access one database. So one application and a second application share the same credentials. Um, there are projects to move forward and remove this security issue. Is to use an API with role-based access and to use only one user for one application and one database, and to move the security layer at the application side. But this project is still running since 2015, so it takes a lot of time. We work on it, but it's not ready yet. So we have to manage the already running application um, for the context. The another solution we can implement is to use one application with only one user. So we basically need to create a lot of users one per application, and this process is not realizable for now because we have not industrialized the database user management yet. So it will be a lot of work to do and to manage on the run. So it's not implemented. Let's talk about security. On Postgres, there is a fantastic technology that we use to prevent or allow connections based on something called host-based authentication, we also known as PgHBA.conf. It's composed of username, an IP address or range, a database name, and an authentication method. And all of those components have to be matched to either allow or reject the connection. And there is one thing here that is a problem for us, is the IP address and range. So let's say we have the following requirement. We have two applications hosted on 3 clients. Here, the first application is hosted on client 1, and the second on the client 2 and 3. And they have to be isolated. Um, for example, the client 1 needs to access the database app 1, and only this client 1 can do so. So for example, the second requirement here is client 2 and 3 needs to be rejected when they try to connect to the app 1. And this database is, for example, client 2 and 3 uh, also have access to the same database cluster, but on other databases. So here, if we allow only client 1 IP address, it will fail because there are load balancers, and IP address of load balancer are not the client 1 IP address. So this IP address here will be rejected. And the second option is to add load balancers IP addresses to allow client 1 to access the cluster. And it will work because the IP address are matched. But what about client 2 and 3? Let's say the client 2 host has been compromised, and the credentials of the client 1 app, or the application 1 app, has been stolen. How to prevent client 2 from connecting to app 1 when they have credentials? We cannot use the PgHBA.conf because the IP address matches, the username matches, and the password matches. But we are not on the same infrastructure. So basically, it will allow the connection where we need to prevent it. In terms of traceability, we have to um, store or record some audit traces. And to answer, when something bad happens, we need to answer very quickly what happens on the system. And to do so, we ask 5 questions, the 5 W's. The first one is the who has done the event. So it's the user identification. It's okay, we have that. It's the username, for example. The what, it's the type of event or the content. It's okay, we have it on the logs. The where, from where it has the event has been detected to where, and here is the problem, um, because of the IP addresses problem. And the when, it's timestamps. We have them all over the place, so it's okay. And the why is why it happened can be deduced by other questions. We can uh, to 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 have more visibility of what happened. We can trace the connections. So if something, if an host has been compromised, we can trace from where um, the host has been connected to the cluster um, for debugging. So we can enable connection, but here in the log entry, we'll see that the client IP here is the load balancer client IP. So the real client IP behind the this connection is not identifiable. Same for disconnections. So when an application connects, um, that doesn't mean the only one query has been issued. We can see that disconnection happens later, so we can log them. And once again, the IP addresses are not the one we expect. Um, let's say we have a downtime on the system um, that has been caused by provoked by an alter or something that can put a lock on a table for an extended amount of time. We we like to see what happens on it. And for security issues, for example, we can trace what password changes um, with by logging DDL. DDL are data definition languages. They are basically create, alter, drop statements, and truncate, and so on. So on this example, let's say a host has been compromised and the password has been known, and the attacker wants to create downtime and change the password and disconnect all the clients, um, we can trace by logging DDL. But once again, the client IP is the load balancer, so it doesn't mean anything. And a slow query. If a query takes a lot of amount of time for OVHcloud, it's few seconds. Um, it may be more for you or less, but for OVHcloud, when we have queries that takes more than 1 second, it can be a problem. So we trace all of them, and for debugging issues, we have not the IP address. We have the load balancer IP address once again. So to solve all of these problems, we can look on PostgreSQL solutions. There is something called the application name, um, which is an arbitrary string that can be set when a client connects to the database cluster. Uh, it's a free um, string, so we can set anything. So at OVHcloud, we manage the client libraries that connect to the database cluster. So we can add this feature and use the application name to store, for example, the source IP address. Um, it solves the login problem. So we now have a way to go back to the real client, but it doesn't prevent some application to connect by using the pghvia.conf rules. So at OVHcloud, we use it, it's good, but it's not solving the problem entirely. So we use it basically it's very useful when we have a containerized environment where every container are hosted on the same uh, cluster or host. So they share the same IP addresses. We can identify containers between others by using the application name, but it cannot be used for security. There is another solution that use the application name, which is PgBouncer. PgBouncer is a lightweight connection pooler for PostgreSQL. It's a very good connection pooler. There is a setting to automatically add the application name for every connection to add the host IP address in the application name automatically. But once again, it's not compatible with pghva.com. And at OVHcloud, we try to use this solution, but we don't need connection pooling because there are some other database connection poolers at the application side. We are able to manage them, so we don't need PgBouncer at the cluster side. And we have unidentified random connection errors by using this this software. Uh, it may be related to our infrastructure. I'm sure it's not directly PgBouncer problem, but we have identified that by removing PgBouncer, the problem is gone. So we decided to not invest more time to implement this solution for the security and traceability part. So there are some generic solutions. The first one we have detected is we use HA proxy, and they have created a standard at the protocol level, which is called Proxy protocol. The idea of this protocol is to use the same thing that the HTTP header, like the proxies for HTTP use, is the X forwarded for header. This special header for the HTTP protocol, record the client IP of the real client IP address. So it's the same idea. There are two forms, the text, the first version, and the binary for the second format. It supports the IPv4 and v6. And one thing, one very important thing for this protocol is that both ends must support it. The proxy must support it, the client one, and the server needs to support it. So it's not only the proxy app has to support the server has to be able to parse this protocol. It's supported by a lot of products, uh, load balancers, HA proxy, of course, web servers like Apache, Nginx, and so on. Even mail servers supported, like Postfix, Dovecot, etc. And what about databases? The MySQL ecosystem already support the protocol, the proxy protocol, like Percona server, MariaDB for the backend and the max scale, for example, for both clients and backends, but not in the PostgreSQL world. Uh, I tried to create a discussion about this protocol on PGSQL hackers, um, and if you and I tried to contribute to PgBouncer to support the proxy protocol, but frankly, I'm not a C developer, and it's very hard to develop in a language you don't know. Despite the way I know some high-level languages, so we try at OVHcloud to focus our efforts to contribute to this very useful feature, but it takes time. So feel free to contribute. It will be great for the community. Or to we are open to discussion, but at OVHcloud it's not yet implemented, so we can't use it uh, by far. There is another solution directly usable by HAProxy. It can be used transparently, but it requires some changes on the infrastructure. We have to tune some kernel settings, some HAProxy configuration, and do some tricks with IP tables and routing, networking routes. For the kernel part, we have to enable the target tproxy setting, and we have to tell the kernel that to allow mounting IP address that are non-local. On HAProxy side, we at OVHcloud we use Debian packages, and it's already compiled with the target that enable the proxy setting, the transparent proxy setting. It has to be run as root because it does something weird on the, not weird, but something advanced on the network stack that requires high privileges. And on the backends, we can use the use author SRC client to automatically convert the its own IP address and port with the client IP address and port, or creating for making a connection to the backend. So client IP and port are now used, as you can see here. But it implies an asymmetric routing. If we stop here, it doesn't work, because when the client would like to talk to the the node, it talks to the proxy that talks to the node using the source IP address and port. So the node will try to get back to the client directly, and it's asymmetric, so it doesn't work. To solve this problem, we have used a second IP address on nodes, a virtual IP that doesn't move. Only we use it only for debugging to ease the traffic because it's very complex. So we move the traffic on an identifiable IP address endpoint on the node. The second step is to mark all the outgoing traffic that has been forwarded to this IP address and port couple. So all the output traffic, all the database output traffic is marked with a special mark here, 1. And we add a rule that says, okay, the mark, all the packet with the mark 1 go to the routing table called here Postgres. So we can now identify the outgoing traffic. And what can we do with this outgoing traffic is to forward this traffic directly to the original IP address, which is the virtual IP that the client expect when it talks to the database. So we say all the traffic that is in the routing table Postgres goes to the virtual IP. And the loop is closed. The client goes to the proxy transforms the IP address to use the client one. On the node, then talk to the node needs to go back to the proxy with the rules, the routing table rules, and the proxy goes to the node, and it's all transparent now. At OVH, we use it since 2 years, and it works perfectly well. We have solved the security and traceability problems. It's very clear now, and we still have high availability. And it's also RDBMS independent. We can use it for basically any clusterized infrastructure. But the downside here is we are DBAs. We are not network engineers. So it's very hard for us when something bad might happen to debug the networking stack because it's a lot more complex now. To conclude, security system, distributed system can be secure and traceable, as we have seen in this talk. PgBouncer is very great for polling. Don't forget it. It's a very mature and good product, but it's not solving our problem. And transparent HA proxy can be hard when you are not familiar with networking stacks, but something very simple uh, can be implemented on Postgres, which is the proxy protocol, and it will be a very, very nice feature for us. Thank you for attending this talk. I hope you have learned something new today. And if you have any question, feel free to ask me them in the chat or go on my website and send me an email. Have a nice day.